Hey everyone, today we're on Unit 5, Lesson 2, more graphing, and then we're going to review some polynomial division. So yesterday we started discussing polynomial functions. In each example, we were given a function to start with, and we identified certain qualities of that function by analyzing it algebraically. Today we're going to work backwards and form polynomial functions based on its graph, hopefully to really understand these components. So things that we focus on. Definitely zeros. Zeros are critical to our polynomials, and those are our x-intercepts. Okay. The multiplicity of each zero. And remember, the multiplicity tells us what happens. Okay. If it's an even multiplicity, the graph bounces. If it's odd, it cuts through. We can have it kind of level off and cut through, and then that's an odd number that's 3 or greater. Our end behavior. Our end behavior is what happens at the end. When it's even and positive, it stays together and goes up. Even and negative, down. Odd, positive, odd, negative. So remember, with the end behavior, it's the degree of the function and our lead coefficient, or our a value. And last thing we talked about yesterday, and we're going to focus on a little more today, is our y-intercept, where it, right, what happens when x is 0, where it crosses the y-axis. And I'm just going to leave that till later on because that's going to help us when we're writing the equations. So our steps to writing an equation: we want to identify from the graph the zeros and their multiplicities. Then we're going to write a factor and then put that in fact, write the function in factored form. And the last step, and this is probably the hardest, is finding the lead coefficient. Okay. So if the y-intercept is 0, we're just going to look at the end behavior, in which case a is going to be 1 or a is going to be -1, depending on if it's flipped. And if the y-intercept is not equal to 0, we're going to use the y-intercept to help us. So we're going to set up an equation and solve for a. So in this first example, if I want to write a polynomial function, and we're going to leave these in factored form. We're not going to worry about putting them in standard form. We're just going to leave them in factored form. So the first thing we want to do is we want to identify the zeros and their multiplicity. So the easiest way to do this is set up our zero multiplicity chart. I have a 0 at -2. And since my graph cuts straight through, we're going to say it has a multiplicity of 1. I have a 0, I have an x-intercept at 0, right? And another one at 1. So at 0, I'm also 1. And at 1, my multiplicity, since I bounce, that means that x-intercept would have a factor of 2. Now, it could be 4, it could be 6, it could be 8. We're just going to stay with the easiest number to work with, which would be 2. So we're going to put these and write these as factors. Now remember, every polynomial function has some sort of lead coefficient out front. So we're going to kind of keep that there. We're going to write that there. So I have a, x plus 2 to the first power, x minus 0 to the first power, and x minus 1 squared. I'm going to shrink this guy up a little bit, meaning this x minus 0 is really just an x. Now, if you think about it, here's the y-intercept part. Here's where it gets tricky. When you have this x out front, if I was to plug in 0, it's going to make everything 0. But that doesn't help me with the a. I need to know, is a 1? So is the graph positive or is the graph negative? That's where I go to the degree of my function. And in this case, if I add up my multiplicities, I have an even degree. So if it's an even degree function, that means my graph can go up, up, or down, down, right? It's up, up if a is positive. It's down, down if a is negative. So in this case, my graph is not being reflected So A is just 1. And that would be the factored form of this function. Let's try another example. I always start by just my zeros first. So I do my zeros and my multiplicities. And I notice right away, all of these cut straight through. So this one's going to be pretty easy to set up. I have an x-intercept or a 0 at -2, at -1, at 0, at 1, and at 2. And the multiplicity at each 0 is 1, because I just kind of showed you that in the beginning. If I write each one of these as a factor, remember we have to include that a out front, that lead coefficient. We're not sure what it is yet. X plus 2, x plus 1, x minus 0, x minus 1, x minus 2. Now, some of you may have already jumped and said, oh, isn't x minus 0 just x anyway? That's okay. Go ahead and do that if you want. Now, I have to go and I have to say, right, this guy here, right? I have to find that lead coefficient, and to find the lead coefficient, I use the y-intercept. The y-intercept and the end behavior, sort of. So I'm looking for A now, right? What is A? I look at my function, add up the multiplicities, because that's going to be the degree of your function. 1, 2, 3, 4, 5. So the degree of this function is 5, which is an odd number. So my end behavior is going to be, this is an odd end behavior. A is positive, A is negative. Now I'm just going to go to my graph and I'm going to look at my end behavior. My left end is going up, my right end is going down. So I have to decide, is my A a positive value or is my A a negative value? Okay, right, when my y-intercept is 0, now I have to just focus on my end behavior. So in this case, it's modeled by that. So for this example, A is -1. I'm reflecting my graph. So you just finish off by substituting for A. And that's your function. In example 3, now this is the first time I'm seeing a y-intercept that's not 0, 0. Okay, so this is we're going to talk about what to do in this case. Always start with your x-intercepts. My 0 multiplicity chart. I have an x-intercept at -1, and that cuts through, so it has a multiplicity of 1. I have an x-intercept at 1, and that one bounces, so that has a multiplicity of 2. Set up your polynomial. A, that lead coefficient, you have to account for it. X minus -1 is x plus 1, that factor occurs once. X minus 1, that factor occurs twice. Now here's where when the y-intercept is not 1, not 0. When the y-intercept is not equal to 0, here's where we have to do a little bit of work. So we're going to plug in 0 for x and set it equal to the y-intercept in your graph. And then solve. So the first thing I do is I rewrite leave A, plug in 0 for x, and set it equal to the y-intercept on your graph, which in this case is 3. 1 times 1, so 1a equals 3. So a equals 3. Now go back, rewrite your equation, rewrite your function, and substitute in the a value you just found. And that's it. Okay, so coming up with the equation just sort of helps us visualize what each component is. We see how important the zeros are to a graph, and most of the time we can factor our functions, or our functions have been given to us in factored form. Now we're going to start the part of this course that we're going to be dealing with things we can't factor. So we're going to have to go to other methods, and another method of factoring is dividing polynomials. We have two types of division when we're dealing with polynomials. We have long division, and we have synthetic division. Each type is going to get us to the same spot. Okay. We sort of need to know both, so I'm going to review both really quickly. Before I begin, let's start with some basic terminology. When we have something, okay, and we're dividing it, the thing we're dividing is called the dividend. So when I give you a polynomial function and I ask you to divide it, okay, we're going to kind of think about it. That's our dividend. What we're dividing by is our divisor. The answer we get is our quotient, and then we always have a remainder. And if you remember from way back when you were just learning about this, the quotient times the divisor plus the remainder equals the dividend. So for instance, just a real easy long division problem to get your mind thinking about long division. If I did 25 divided by 4, I'd put the 25 underneath, the 4 on the outside. 4 goes into 25 6 times. 6 times 4, 24. I subtract. I have a remainder of 1. If you were doing this problem in 4th grade, your teacher would have said, oh, check it. How do you check it? 6 times 4, 24, plus your remainder is 25. So it's just a real quick reviewing the steps, because I need you to remember, what your steps are and where to put things. Now we're going to deal with something a lot messier. I want to find the quotient and remainder, and we're going to sort of change things a tiny bit, how we write our answers from what you did last year. Okay, so I'm not going to get as nitpicky as some of your Algebra 2 teachers may have gotten. The quotient and the remainder, so what am I dividing? What goes underneath, right? That's my dividend. So I'm going to put this, set up my division bar, 3x cubed plus 4x squared plus x plus 7. And my divisor, what I'm putting out front, is the x squared plus 1. This is what I'm dividing by. Now, even though it's more complicated, the process is the same. Okay, so we just have to think about what's important. This guy out here, this is important, and this is important. So we're always going to focus on the biggest things first. So how many times does x squared go into 3x cubed? Or you could think about, what would I have to multiply by? So I would multiply by 3x to get 3x cubed. Don't worry about the 1. Okay, that guy will follow along. Always just focus on that first big term. Now we're going to do the multiply process. 3x times x squared gives me 3x cubed. And now, since we're multiplying a quantity, we have to also do 3x times 1. And we're going to be careful here because we are going to be subtracting, so we're going to line it up. We're going to line it up under the right column. Now the next step is going to be subtraction. Remember, you're subtracting that quantity. So I'm going to negate and negate. I'm minusing. If one of these happened to be a minus, you would add it. You would plus it. Bring down. Subtract x minus 3x. Bring down the 7. Now we start the whole process again. This time, how many times does x squared go into 4x squared? Plus 4. 4 times x squared. 4 times 1. Subtract. That's going to turn to 0. I'm going to get a negative 2x plus 3. How many times does x squared go into negative 2x? It doesn't. So this is your remainder. So I have a quotient of 3x plus 4. Remember, that's going to be what's on top. And I have a remainder of negative 2x plus 3. If I ask you to identify the quotient and remainder, that's good enough for your answer. Okay. That's okay. We're going to check this one. We're going to check our work just for this example. And remember, when we check our work, we're doing quotient times divisor plus remainder. So I'm going to write my quotient, which is 3x plus 4, times my divisor, plus our remainder. And if we work out this math, we should get what we originally had under the division bar. 3x cubed plus 4x squared plus 3x plus 4 minus 2x plus 3. And if you see that, it does match. Now you could practice this for any of your homework questions or whatnot, but I'm okay with you, as long as you understand the concept, I'm okay with you just identifying the quotient and the remainder. Now, one thing we could say about polynomial division is long division is it's very useful. It helps us, but it's time consuming and you can get messed up with the x's. So an easier way, and something you learned last year, is something called synthetic division. And with synthetic division, we sort of take all of those x's out of the way and we make things a little bit easier for us. So with synthetic division, we're going to do the same thing. We're going to get the same result, but we're just going to kind of do it a little bit quicker. Okay. The only downfall is with synthetic division, you can only divide by what we call a linear factor, meaning x has to be to the first power. I could not have used it for this example. X cubed minus 4x squared minus 5 divided by x minus 3. So this first step of synthetic division, and because we're doing sort of a cheating thing, I do my division bar like this. I'm going to write the coefficients without the x's. I'm going to write the coefficients of each term in this bar. So in front of the x cubed, I have a 1. In front of the x squared, I have a negative 4. Now be careful. I go straight to negative 5. So I'm missing the x term. So we have to do a placeholder. And then negative 5. So step 1 would be to write coefficients of each term. And remember to be careful. If you skip a term, put a 0. Now I have to figure out what I'm dividing by. And we're kind of cheating, we're working backwards. So if my factor is x minus 3, I'm dividing by 3. My x-intercept is 3. So we're going to put 3 on the outside. Bring down the first number, don't do anything with that. Now I'm going to multiply on the diagonal. I don't know how to spell diagonal. I hope that's right. And we're going to add on the column. 3 times 1 is 3. Negative 4 plus 3 is negative 1. 3 times negative 1, negative 3. 0 minus 3. 3 times negative 3 is negative 9, and I get negative 14 as my remainder. So here, my quotient, now I have to figure out what my quotient is. Remember, your quotient would be up here, what you divided by. My quotient doesn't have any x's in it right now, so I have to put them back in. So when we put our x's back in, think about what happens. If I have x cubed and I divide by x squared, do you see how your quotient goes down? So we have to figure out how much does this go down by. And typically, since we're just dividing by x, we're going to go down a power. So when I put my variables back in, this is going to be x squared. And now each term I go down a power. Minus x minus 3. And my remainder is negative 14. This is going to be a number. Okay, that's always going to be a number. Does that make sense to everyone? Now remember, really what we did was we just broke this up into that, that, and that. If we multiply all that together, what do we get? Right? We're going to get what we started with. Let's try another example. So I'm dividing this by this. So my first step, I'm going to take the coefficients out. 2x cubed, 2. 1x squared, 1. Negative 13x, and positive 6. This was nice because it went down nicely. It went down each power. I don't have any zeros. Now, remember, we have to be in the form of x minus r. This is in the form of 2x minus 1. So we have to adjust this. So basically what I would do is to find the number to divide by. I'm just going to find what the x-intercept would be. So 2x minus 1 is the same as x minus 1/2. Okay, they mean the same thing. So the number I'm going to divide by is 1/2 out front, my x-intercept. Bring down my 2. 1/2 times 2 is 1. 1/2 times 2 is 1. Negative 13, that's negative 12. 1/2 times negative 12 is negative 6. And this time my remainder is 0. When I go to put my factors, but my x's back in, I get 2x squared plus 2x minus 12. This is our quotient, and I have a remainder of 0. But I do want to point out, remember what this means. This means that 2x minus 1 times 2x squared plus 2x minus 12 plus 0 is going to equal the original. So this is kind of a special thing because now we know that this is actually a factor and could use it to divide. And help factor the original function. We're going to work on that more tomorrow. Okay. Today we're just going to do one more example practicing. Actually, I'm not even going to do it. Okay. Because it's just another long division. Okay. I'll work it out. I'll work it out very, very quickly just to show you. How did I know it was long division? X squared plus 2, and I have no way to rewrite that as a linear factor. So really quickly, I'm going to work through this one. But our focus in our class is going to mainly be with synthetic right now. 1, 1. Oh, I can't. What am I doing? Stupid. I have to use long division. I'm not going to talk. I'm just going to do the math for it. Okay, so there's your work for that. And you have stuff to look back at. Please practice your homework tonight. And thank you for joining in.